Good day to you all, wherever you are. I see we've got people in Toronto here, we've got Rome, we've got India, we've got Wales, Warrington, Tamworth, and even London. So from dark Bedford, welcome to this evening's talk. For those who don't know me, I'm Alistair Scott, a past president of the Society, but now as chair of the events committee, I try to keep all our events up and running, and I'm always looking for new talks and more futuristic talks as well. Welcome to the British Interplanetary Society's 16th live streaming evening lecture since March, April of last year. Our next event, our Beyond the Moon Symposium, is on the 12th of April, which is Cosmonauts Day, and we'll also be celebrating the 60th anniversary of Yuri Gagarin's historic spaceflight, both during the conference and at Yuri's night party afterwards. The provisional program is now out, so book your places as soon as possible. Of course, both the conference and the party are virtual, but I understand the conferencing platform we're using is brilliant and will allow you to meet up with everybody at the coffee bar to start with and skip in and out of the real bar at any time during the day. Sadly, both the coffee and the drinks will be virtual too. Tickets are now on sale for our Reinventing Space Conference in the QE2 Conference Centre in Westminster on the 28th to 30th of June. We hope it will be face-to-face, but we don't know, and we'll have to incorporate social distancing if necessary. Now, if I have time, I'll talk more about these at the end, but also tell you more about the conference or the other evening lectures we've got lined up. Today, we are again using Crowdcast for both the presentation and the Q&A. It worked well last time, so let's hope we have a trouble-free session tonight. If you enjoy this evening and want to make a small donation, please click on the donate button at the bottom right-hand side of this page. Every little helps to cover the cost of these lectures. Please use the question and answer system to your questions anytime during the talk. And as most of you know, you can also vote for those questions you really want to hear go to the top of the list by clicking on the vote button. I'm pleased to say that we have tonight with us Francesco Castellini from ESA ESOC, and he is going to tell us all about the flight dynamics operations for the ESA deep space missions. I'll hand over to Fabrizio now to do the introductions and get the show on the road. Over to you, Fabrizio.
Hello, Alistair. Thank you a lot, and thanks to everybody for attending this lecture. Especially thanks to Francesco Castellini for being with us for this lecture, or for offering this lecture to us. Francesco is a long-standing member of the BIS because actually we just lost him. Okay, he's back. Okay,
yes.
I saw him disconnected for
I think there was a problem with my connection, but it seems fixed now. Sorry.
Okay. Let's hope it stays like this.
Yes.
You know what? We don't accept the double failures in our. A single one is enough. It's in our environment. It's usually like this.
I have disconnected the VPN. Sometimes it makes problems with the connection. So now I'm on my line normal. So I hope it works fine.
Okay. Okay. So Francesco is a long-standing friend of the BIS. He came twice in Rome on his own time, on his own money, to give lectures at our university organized by BIS Italia. And his lectures have always been very long, very enthusiastic, very interesting. And I can really testify that some students, even high school students, decided to approach our aerospace engineering or other engineering because of his lectures. So I think it's very important he does this lecture for the BIS as a whole this time. It's not going to last 2 hours. So luckily this time it's going to last probably 1 hour. We have time for questions, of course, so use the button below. So Francesco graduated from the Politecnico di Milano, of which I'm happy to say that I started my university career there. So we share a little bit of the same rooms. and he got a Master of Science and then also a PhD in Aerospace Engineering, working on launchers. And he has more than 10 years of experience in work in the sector, and he works launch system, mission operation, and flight dynamics and navigation. So today we are talking about flight dynamics because Francesco works in the flight dynamics section of ESOC, the European Space Operations Center. We had a previous talk by Paolo Ferri, the head of ESOC, and he introduced us to the flight control, which is the other world of the operation. Francesco is from the other, let's say, the other side of the fence, flight dynamics, and especially works in software development, mission preparation, and operation for all ESA deep space missions. I met Francesco talking about Rosetta. He was enthusiastic about Rosetta at that time, the first time. I don't know if he's going to talk again about Rosetta, but I'm sure that he's going to talk also about the newer mission we have flying now. So I will now give let's say the presentation, the control of everything to Francesco. Please do your question on the Q&A using the Q&A link below the screen. You can do that during the talk so you don't forget the topic you want to address. And you can vote the questions, so you can have the most important question answered first, and I will meet you all at the end of the presentation. Thanks again, Francesco.
Yeah, you're welcome. So now I can share the screen, no?
Yes, you can. Let me see if everything works.
Yeah. So if I do that, you should be seeing the presentation. Yeah?
Perfect. Perfect.
Okay.
Yes.
Then I start. Okay, so good evening, everybody. Yeah, I'm gonna try to give you a brief, more or less, introduction on what flight dynamics means and what we do at ESOC here in Germany. And I'm gonna focus on deep space missions because this is what I work on. And yeah, okay, this is a topic where I could probably talk for hours, so I will try to fit in 1 hour, which is always difficult, and but I will try to do my best. And then I will probably touch a few topics very quickly, and if you have questions, you can always ask me. So I would like to start giving a very quick introduction on the ESA deep space missions in general. I borrowed a few slides from the ESA templates, but that's going to be very fast. And then going a bit more into the details of flight dynamics operations and what we do in flight dynamics to support all the ESA missions, and what we call the flight dynamics cycle, which is the operational cycle, that all the steps that have to happen such that we go from understanding where our spacecraft is, optimizing its trajectory so that it goes where we want to go, and generating the attitude and maneuver-related commands, and then monitoring that the spacecraft is actually doing what it's supposed to do. And then I thought about having multiple examples, but in the end I realized I would not fit in in 1 hour. So I have put here today again the Rosetta mission because I think it's the most interesting, let's say, and because it gives a very wide overview of all the possible activities that we do in flight dynamics. But I will also give a few, maybe mention a few other missions that are in operations now and that will be in operations also in the future. And then if you want to ask me some questions about these other missions, of course, there is no problem. So here, okay, these are all in the bottom, just old missions that are not flying anymore, but I wanted to start with the history of ESA and where the interplanetary missions of ESA started, which is back when, okay, just after I was born with Giotto, and then going along and reaching Venus Express, which is the first mission that I've actually been working on. And then you probably all know that we went on Titan with Huygens quite a long time ago, and then and then the other big landing that we did was Rosetta, and I'm gonna tell you a lot more about this later on. Other interesting missions that you may have heard of are the Exomars missions. We are now operating TGO, the Trace Gas Orbiter, which is in orbit around Mars, and it's working very well. And we'll be soon launching Exomars 2022. So basically the rover that is hopefully going to land and explore the surface of Mars. And these are just basic screenshots of what I thought were the most interesting missions to mention that are being operated right now. And here also from one of the ESA slides, there's a nice view of all the ESA missions in the solar system. I've circled the ones that I've been working on directly. So, okay, as I said, I will say quite a bit more about Rosetta, but these are all the other missions that we are flying. Also, JUICE will be a very interesting mission that will come soon. We should launch in September 2022. And actually, it's I was describing at the beginning and saying deep space mission. Okay, that is a bit of a terminology matter. So at ESA, we are mostly talking of science missions, and for this we consider both those that are in interplanetary space and those that are doing observations of stars, galaxies, and so on. So right now we are operating Gaia, which is doing a very nice star catalog with very high accuracy, that much more than what was previously available. And we've also flown LISA Pathfinder recently, and we will launch soon Euclid. But okay, this was just to give you an idea of what and how many are the science missions of ESA. And here I've put just one quick slide on the Science Operations Center, because today everything will be focused on ESOC, which is European Space Operations Center here in Darmstadt in Germany. But yeah, just to say that there is also the other counterpart of our work, which is focused on operations, but for the science part, and this is in Madrid. So here in Madrid, there are the people that coordinate the work of all the scientists throughout Europe and also outside of Europe that provide the payloads to our spacecraft. So this was really quickly. So what I'm now going to do is to introduce operations, but since there were already other talks and it's not really my field, I will not talk much about the flight control team part, which is what Fabrizio was saying before. This is the one part of the operations that are done here at ESOC, and in particular, there's for each mission there is a dedicated team, which is called flight control team, which is only following that one mission and takes care of everything. Is the main responsible of all the operations and all the interfaces with the scientists and with the rest of the world. And then I'm going to discuss more in details the other side, which is flight dynamics. And okay, this is again one of the usual ESA slides. And then besides flight dynamics, so flight dynamics is basically one of the multi-mission support teams. So this means that for each mission there is a flight control team, but then and then on top of these flight control teams, there's a wider group of people, several teams that give support to across the missions. Flight dynamics is one. Ground stations engineering is another one. For example, there's a group of people again here at ESOC that takes care of all the ground station related systems, but also there's people focused on software and so on. But flight dynamics is what we're going to discuss today, and in particular what we do for interplanetary missions. So spacecraft operations. This is what a brief schematics of spacecraft operations at ESA looks like. This is an example from Gaia. This spacecraft here is Gaia, and you see there's okay, a few boxes here and there. We have one big box on the bottom left, which is the Science Operations Center, which I mentioned earlier at ESOC. They are the ones that coordinate the scientists and have an interface only with us at the Mission Operations Center. And the Mission Operations Center has instead interfaces with all the ground stations, which are our way to talk to the spacecraft, of course. And the spacecraft talks directly to the stations that are located around the world. Actually, this was a screenshot of the current ESA ground stations. We have 3 big antennas like this, 35 meters, spaced 120 degrees roughly in longitude to be able to access the full sky at the same time. And then many other smaller antennas that are used mostly for either Earth orbiters or for the launch phases. And so our spacecraft talk to the ground stations, and the ground stations talk to us. And us in the Mission Operations Center, we have here several components. We have a mission control system, which is the one handled by the flight control teams to receive the telemetry and to prepare the commands for the spacecraft. We have other tools like simulators and mission planning systems and so on. And we have the flight dynamics system, which is embedded in the MOC, in the Mission Operations Center, which is located here at ESOC. And as I was mentioning, flight dynamics. So this is a picture that somebody took because I was here, so it was not me taking it, of the flight dynamics room. This was during the final descent to the Rosetta comet in 2016. And flight dynamics gives support to all missions. We are split in 2 main teams, one giving support to interplanetary and science missions, and where I work, and another one giving support exclusively to Earth observation missions. And we are involved in basically all the steps of ESA missions. So we start from the very beginning with helping in the mission development. So especially we participate in reviews and tests at the spacecraft for what concerns the interfaces with flight dynamics and what flight dynamics can give in terms of expertise back to the design. And we participate in the ground system design, in the ground segment design, because flight dynamics is part of the ground segment. And we participate in the operations preparation, so simulation campaign, mission readiness tests, which are tests with the ground stations, launch campaigns, of course. And then we are at the center, together with the flight control teams, of all the critical operations. Critical operations are all the operations that require live interactions with the spacecraft, and often 24/7 for a brief period of time. Like the LEOPS, launch and early operation phases, or the commissioning phases as well, and all the other critical events like when we do a flyby, the targeting and the flyby phase, or landings, of course, or when we have to target for a Mars orbit insertion, or all of these things. And we participate also in all the routine operations, which are instead usually made offline. So this means that there is no live interaction, but there is still a lot of activities that go on a normal, usually weekly planning pattern for taking care of orbit maintenance, but also of science planning and science execution, and onboard the OCS systems maintenance as well. So all of this goes into a big, let's say, chunk of expertise that we have built here at ESOC in the flight dynamics section. And it's actually quite important to be able to feed back this expertise into the design of new missions. So this is actually why it's important that flight dynamics, even if we are fully operationally focused, so we're not designing the spacecraft, it's very important that we are included in the early design reviews for new spacecraft, because this way we can give some hints and help in some things, to such that lessons learned from operating missions are fed back into the design of new ones. So this is more or less all of the activities that we perform. But I would like to focus and to give a description of what are the main tasks, and to do that, I want to take the operational approach, so tell you what we do in operations, and then everything else that we do, so in development and design and so on, basically falls within the same categories. So if I describe to you the way that we do operations, you can also imagine how we do the development and the design phases before. So we As I already mentioned, we are split between the Earth observation support and the science mission support. And these are two of the four sections in the flight dynamics division. There is two more sections. There is a mission analysis section, which is a bit split because they are actually in charge of all the mission analysis work, so trajectory design, trajectory optimization, and so on, which is done at the beginning of the mission. So this is an input to the mission design. So I will not discuss this today. And then we have a last section, which is actually very important for operations, which is called test and validation. And this is a separate group of people who are in charge of checking that everything that comes out of flight dynamics is correct, or at least not hopefully wrong. And I will talk a bit more about them later because they are very important. So we are, all of these people, we are sharing the same hardware and software, basic software infrastructure. So not the application software, but the basic software infrastructure. And something that is very important to us is that we are using only software that we develop internally. So we don't buy software from companies. We almost nothing, let's say. All of it is software that we develop and we design, we code, we test, we validate, we bring into operations, and we use in operations. And this is very important because it's the only way that we have direct control and understanding of what is happening in the code. So this is the way that whenever there is a problem, we can debug it on the fly and really know what is the problem very quickly, and even fix potential problems very quickly, because this way we don't have to have an external entity like a company outside that we have to send the bug reports or whatever and take time to iterate. So this is for operations, it's really critical that you are able to fully understand what your software does and be able to quickly react to any required changes. So this was in general, and now going a bit more in particular. This division that I show here, it's between the four main disciplines that we have in flight dynamics. At least at ESOC, we are split like this. We have four teams, one called Orbit, the other Maneuvre, Attitude, and Command. The Orbit team, which actually is the one where currently I am in, is in charge of the navigation of the spacecraft. So basically the orbit determination and prediction. I will give quite a few details more later. Then we have a separate team doing maneuver optimization, which means once they have taken our inputs, so the inputs from the orbit determination, so basically they know where the spacecraft is thanks to the work done in the orbit team. They are in charge of optimizing the maneuvers in the future, such that the spacecraft follows the trajectory that is planned. And a priori, so the preparation phases of the mission, but also during the mission itself, they are also in charge of trajectory planning. So to basically agree with the scientists what are the targets of each mission, and to define what is a long-term orbit, which is our reference orbit to be then followed in operations. Then we have an attitude team. I was actually in the attitude team for several years in the past, and the attitude team is in charge of monitoring the spacecraft. So, of course, the flight control team for each mission is the main actor in checking that the spacecraft is fine, but they do not have very deep expertise in the attitude dynamics and orbital dynamics that are sometimes required to do very detailed checks. So we are basically with the attitude team in charge of monitoring the AOCS related parts, and we do both real-time and offline anomaly analysis, which means real-time, if we are in critical operations, there is a problem, we have to solve it, and this is something that is needed very quickly, or offline, because if it's in routine, we can take a bit more time. And then at the end, we have one more team, which is the command team, and they are in charge of taking the outputs from orbit and maneuver, and basically knowing what is going to be the required trajectory in the future, and knowing what are the requirements from the scientists in terms of where we have to point our spacecraft. They are in charge of generating all the commands that are then going to the spacecraft through the flight control team to steer the spacecraft both in terms of orbit and in terms of attitude. And as I mentioned, we have a test and validation team, which is split in 2 sub-teams, test and validation orbit and test and validation attitude, who are in charge of checking all the outputs of the orbit and maneuver subsystems and of the attitude and command subsystems. So this is the way that we operate, and this is quite important to understand all the details of what we call flight dynamic cycle that I will describe in a second. And okay, this is to show you flight dynamics kind of as a black box. So you have here flight dynamics with some random picture from some time ago during some LEOP, I guess. I don't remember when this was taken. And with the 6 subsystems, let's say, orbit, maneuver, attitude command, test and validation orbit, and test and validation attitude. And here are with our main interfaces to the external world. So I already mentioned flight control teams. They are our main, let's say, partners in the operations of a spacecraft. But we also have very frequent interaction with the science ground support at ESOC in Madrid for all what are the requirements, so the requests of the scientists for what we have to fly, so which orbit we have to fly and which pointings we have to fly. And then, of course, with the ground stations, because telemetry and telecommand, of course, need to reach the flight control team first, but then also flight dynamics, so that we can check, for example, the telemetry of thrusters to see that everything is fine. But not only for that, we also use the ground stations for tracking. So the orbit determination is done based mostly on ground station tracking data. So I will describe them a bit later. And then we have also some interfaces with external partners, so completely external to ESA. For example, I've put here the Jet Propulsion Laboratory in Pasadena from NASA. And it's not the only external partner that we have, but I've put it here because, okay, it's fancy, but also because in flight dynamics, we have a very long-standing collaboration with them. So we've been collaborating with JPL since probably the end of the 90s. And because in the end, they are the ones that do the same flight dynamics work for the NASA missions. And we have a lot of exchanges, both for validation of software, for actually interest in some of the missions. So interest from our side on their missions and the other way around. We also provide tracking support with our ground stations to NASA missions, and the other way around, NASA is providing tracking support to our missions, and therefore we need, for example, when we track a NASA spacecraft, we have to check that the tracking data that we receive from our stations is correct before sending it out, and the other way around, when we receive the tracking data from NASA DSN, then it's them checking that the data is correct, and we receive their data. And also for some missions, we have done shadow operations. This means that, for example, we are doing the main orbit determination for Rosetta, for instance, or for Exomars during aerobraking, but JPL is doing a parallel orbit determination with their own completely separate systems, and but using the same input data, the same measurements, and then we can compare the solutions. And since deep space orbit determination is sometimes very, very challenging, and it's difficult to verify that the solutions that we obtain are correct, to have this kind of shadow navigation is really a very strong point to avoid that there are critical errors. So yeah, this is a bit of the flight dynamics black box. And then this is a bit instead of a white box, so showing a bit more in details the interfaces and what we call flight dynamic cycle. So flight dynamic cycle is what you see in front of you. This is done for every mission. So every mission has this kind of exchange of data and computations that needs to be done in order to fly the mission. And there are differences, of course, between the different missions, but the basic structure remains the same. What changes very often is the frequency of this cycle. So sometimes we can do this only very rarely, like, I don't know, once per month. For example, if we are with a mission which is in deep space, doing nothing, basically, just flying towards wherever we have to go. Like it could be now for Bepi Colombo, for example. We are not, we have done 2 flybys already. We will do many more flybys, but right now we are in a quiet deep space cruise. And in this phase, we don't need to do to update the commands on board the spacecraft very often, so we do this monthly. For missions in routine operations, for example, Mars Express or Exomars or on Mars, that we are doing routine scientific observations of Mars. This cycle is done once per week, for example, because every week the scientists want to send more commands, and these commands must be with the latest possible knowledge on the orbit of the spacecraft. So we have to do this update every week to send the commands that are in sync with the reality of what the spacecraft is doing. This happens the same also for Gaia. So most of our missions, once they come into routine operations, we have this cycle which is done weekly, also because this way it's easy to adapt to the working week of people here on Earth. And but okay, for some cases, in some mission phases, we have to do this even more frequently. So for example, for Exomars, we did the very challenging part, which is the aerobraking. We were using the atmosphere of Mars to lower our orbit from a very elliptical orbit with a high apocenter down to a circular orbit very close to the planet. And to avoid using propellant for that, there was not enough propellant. It was designed like that. Then we did aerobraking, and aerobraking is a critical phase which lasts very long, but it's very challenging because we have to make sure that the spacecraft doesn't get burned in the atmosphere. And this requires that we do, since the atmosphere of the planets, in particular the one of Mars, but even the one of our Earth would be unpredictable. So we cannot very well forecast the weather here on Earth. For sure, we cannot do it at all on Mars, which means that we have to check every day what the weather was on Mars, so how much the density of the atmosphere was at the time of our pericenter passes, such that we can basically reconstruct the actual orbit followed by the spacecraft and predict the orbit for the future, and prepare the maneuver commands such that we can tune the altitude of the next pericenters to be in the let's say, small corridor that is good enough for doing aerobraking. Because if we fly too high, then the spacecraft doesn't aerobrake, so we will never reach our target orbit. And if we fly too low, we risk exceeding the thermal limits of the spacecraft. So in this case, we were doing this flight dynamic cycle every day. So basically, this can go from every day to every month, depending on the mission and the mission phase. But no matter what the frequency is, the sequence is always more or less the same. So we come in with information from the scientists and from the stations. So tracking data from the stations and pointing requests from the scientists. We have a preliminary step usually, which is only needed in some missions, which is done by the attitude team. So basically, the attitude team is in charge of monitoring the spacecraft, but also processing telemetry. So for example, for some missions, we need as an input to the orbit determination, some data from the telemetry, like how much the thrusters have fired, which is important because it affects, of course, the orbit. Or for aerobraking on Exomars or on any other aerobraking mission, we wanted to have the accelerometer data to know what the delta V given by the atmosphere in a given atmospheric pass was. And these kind of things that are extracted from telemetry, they are processed by the attitude team, and such that the orbit determination system can then ingest them. And of course, at the bottom here, I've put optical data processing. So basically, in some missions, so far only Rosetta, but we will soon have Hera going to an asteroid, and also for JUICE, we will use optical data. So basically, whenever we need to do relative navigation with respect to a body, and we use the onboard cameras to take images of that body, and we use the images taken from on board to detect features on the bodies such that we can know where we are with respect to those bodies. There is a big part of the work that is done by the attitude team, which is processing those data, so doing image processing to extract the information from the images. And as you can imagine, it's quite complex because, yeah, okay, I will show you a bit more later. So the first step is to process telemetry if it is needed, pass it to the orbit determination. The orbit determination system takes all the measurements from the stations, so the tracking data, range and Doppler, mostly from the stations, as well as the information from telemetry and from other things. And we put everything in this orbit determination filter, which spits out what is the orbit, the past orbit of the spacecraft, but also parameters of the dynamics that allow us to predict the orbit in the future. Then we give this information to the maneuver team. The maneuver team takes this information, both the predicted orbit, but also the predicted dynamic parameters. For example, this could be the scaling of the atmosphere on Mars for the aerobraking, and uses this information to optimize the trajectory for the future. Then it generates another orbit, which is not only the reconstructed part for the past or the predicted part for the future, but it's actually the predicted part, including the maneuvers that will have to be executed, and passes this information to the command generation group. The command generation group uses this information from the desired maneuvers that are going to be done in the future, as well as all the requests from the scientists for the pointing of the spacecraft, and generates the commands for the spacecraft itself. And then there is another auxiliary step at the end with the attitude team that needs to generate what we call auxiliary products. These are a set of files that are needed by either the flight control team or the scientists or somebody else, let's say, and that are based upon all the chain of events before, let's say. And then the outputs of this big box, so not only the outputs of attitude, but the outputs of the whole flight dynamics, are to the flight control team. Of course, we have to send to the flight control team the commands, because they are the ones that are going to merge the commands from the spacecraft, from the OCS part generated by flight dynamics, with all the other commands from the other subsystems like TT&C or power or thermal or whatever. They merge all the commands, they prepare them through a mission planning system, merge them also with the commands of the payloads, and then send everything to the spacecraft. We also have direct interfaces with the scientists. Some of these auxiliary products are needed by the scientists to, for example, to take the science out of their raw payload data. For example, they might want to know exactly where an image was taken from, in order to be able to know what they observed in their image. This is a simple example. And again, we have to send outputs to the stations, because the stations give us the tracking data, and the stations uplink telecommands and downlink telemetry, but only if they know where they have to point. So we have to tell to the stations, again, where our spacecraft will be, what will be the predicted position and velocity of the spacecraft, such that they know where they have to point in the sky to be able to track the spacecraft in the future. So yeah, this is the whole cycle of activities. And here at the bottom, I've put some more details on what is needed for small body missions like Rosetta or Hera. And in these cases, there are more things to be done, like estimating parameters for the small body, or planning the trajectory in more details, because when you're flying around the small body, you are not constrained by the initial orbit. So basically, when you are flying around a planet, once you are in orbit, okay, you can slightly tune this orbit or change the phasing around the planet along that orbit, but you cannot really change a lot the orbit because we don't have the propellant. But when you are around a small body, where all the velocities are very small, then you can basically invent your own trajectories fully. And that's really a lot of fun to be done. And yeah, the last thing, okay, modeling of the coma, for example, for Rosetta again, and also again for missions where we do imaging. Another very important thing is that we are the ones in charge of commanding the navigation cameras. So we don't want the navigation camera commands. So really, how to take pictures, like exposure times and filters and so on. We don't want this to be done by other people, because we know exactly what we want and when we want it. So this is a very dense description of what we do in flight dynamics. Now, we are already, I think, out of time, so I have a lot of slides, but as usual, I cannot go through them all. But I wanted to spend some time on this slide because I think it's very important to understand what flight dynamics means actually, and then we can go a bit more into the fun part with an example. And I will skip a bit of these slides. The only thing that I want to mention again that I've told you about this for interplanetary missions, but Earth observation missions do exactly the same. They just have some shortcuts, let's say, because some things are simpler for them. But actually, what they have in terms of easier life for some things, like, I don't know, in the orbit determination, they have GPS data, which is much easier than to do the orbit determination with that, for example. But in turn, they have a lot of complexity in the automation, because for us, every mission is a single mission that needs to be developed almost from scratch and so on. But for them, the problem is that they have a lot of missions. So they have tens of missions while we only have few. So for them, for the ESOC flight dynamics team, for the Earth observation missions, what is critical is automation, to be able to run all the missions that they have to run. And then here, the test and validation team, I briefly mentioned it before, and I'm not going to describe it longer later, but I really want to stress how important this is, because in ESOC, flight dynamics has a very good name, let's say, because we very rarely make big mistakes. But this is not because we are very clever, let's say. This is because everything is very procedurally defined, and we have the test and validation team that allows us to have confidence in our results. So basically, all the teams are doing their work, but then there is a test and validation officer, so a guy that does not really the full calculations again, but at least checks that the outputs are consistent, and they do this with completely separate software tools, completely separate methods, and completely separate people, such that the likelihood that two different software with two different people and two different methods are actually doing the same error is quite low. So we minimize the risk like that. Of course, it's a big overhead in terms of work, but it's really a key part of ensuring that flight dynamics products are correct. And this is very important because if you make a mistake in a maneuver, okay, in some cases it's not a big deal, but in some other cases it can mean the death of your mission. So if you move the pericenter, going back to the example of Exomars, if you move the pericenter 5 kilometers down instead of 5 kilometers up during aerobraking, you might kill your spacecraft. So it's really critical that what comes out of flight dynamics is not awfully wrong, and test and validation is what is one more thing that allows us to try to ensure that. So since it's already 7:45, I think I will skip the slides describing the separate subsystems because I don't have the time. And I want also to give you some information on a practical example rather than just showing you the inner workings of the subsystems. But okay, I have quite a few more slides that I think I can distribute this. I will have to check, but you can always ask me later if you want. So this, you can see it's a bit of slides about the single subsystems. So the ground navigation workflow with the work done by the orbit determination and the maneuver optimization people, and the details of orbit determination, how we do it, the fact that we have, okay, this is an example of how the outputs of our orbit determination look like. So here it's residuals, so the difference between what we compute from models to be the two-way Doppler effect, which is the line of sight velocity of the spacecraft with respect to our ground station, and the actual measurement. So you see that this is a noise in the order of 0.1 millimeter per second. So this means that we are capable of fitting the data, and the data as a noise that is in the order of 0.1 millimeter per second. So this means that if we have a spacecraft around Mars, we know with 0.1 millimeter per second accuracy along the line of sight what is the relative velocity with respect to our ground station. And okay, there are differences here depending on the band that we use. So Ka band is better than X band because it's higher, but okay, these are details. And here on the right, you have instead range residuals. So the same thing, but for the range data instead of Doppler data. So here we're talking about a few meters of differences, and these jumps that you see are mostly due to uncalibrated errors in the transponder delays. So basically you have a signal that originates from the ground station. The signal goes to the spacecraft. The spacecraft transponder takes the signal and brings it back to the Earth. And there is a delay in the electronics of the spacecraft, this transponder delay, which is not perfectly known. And this results in small differences when changing, for example, equipments on board. So this was from a commissioning period where we were switching, for example, the antennas on board or the transponder on board. And this is seen in differences in these delays. But okay. Maneuver optimization, again, they optimize the maneuver. Commands, they generate the commands. Here are some examples of how we monitor the spacecraft. So like different things that come from the telemetry. And all these things have a kind of old feeling, old touch with the GUIs that are a bit old. But okay, we are in the process now of modernizing fully all the flight dynamics software. So in a couple of years from now, maybe these graphs will look more modern, but for the time being, they are like this. And this is a very nice example of how we monitor the star tracker, which takes continuous images of the sky to fit the stars and to basically tell to the onboard software of the spacecraft where the spacecraft is looking at. So what is the attitude, the three-axis attitude of the spacecraft. And we monitor this by looking at what are the expected stars in the catalog, which are the white boxes, and what are the positions on the CCD that are returned from telemetry, which are the red crosses, for example. And this one was the limb of a planet coming into the field of view. And okay, this was just some examples. But now, since I only have, I think, 20 minutes left, I will go to an example. I have a lot of slides on Rosetta, and I will not go through the details of Rosetta because maybe you know about the mission. It's probably, at least personally for me, the most exciting missions I've worked so far, even though all the missions are interesting. But okay, since Rosetta also has all these pictures and optical navigation part, I think it's more fun to talk about this than other missions right now. So you know about Rosetta, you know about the target of Rosetta. This was how they thought, the scientists thought that the comet 67P Churyumov-Gerasimenko would look like before getting there. And this is how it actually looked like after getting there. So this was quite a surprise to see the comet like this. This is the spacecraft. I'm not going to spend time on this, but this is how we see the spacecraft. So a bunch of units and thrusters and star trackers and cameras and so on. And but what is important is this one here. So these are the eyes of Rosetta. These were the eyes of Rosetta. So the navigation cameras and the scientific cameras. And these were our bread and butter every day. We were looking at the images and doing optical navigation on these images. And therefore, it was very important for us to know the performances of these cameras, like, you know, the performance of your reflex if you're taking images on Earth. You have also to know what are the performances of your cameras on the spacecraft. So this is how we first detected the comet. You see here months before arriving, the comet was already visible, and there was even an outburst from the coma. This was from millions of kilometers away, and the comet was subpixel, but the coma itself was not. So you see here that what was split by the comet became visible as a very bright coma tail in the pictures. And this is what it looked like when we got to 12,000 kilometers away, when the comet was actually 25 pixels on the narrow angle camera. And this is the moment where we started to realize, okay, there is something weird about this comet. And okay, this I think I can skip. It's a long video from ESA about the trajectories that we flew. We flew these weird triangular trajectories from 100 kilometers distance at first, and then from 60 kilometers distance to observe the comet and understand the physical properties, both the gravity and the rotation axis and the shape and all of this, before we could go down, because you have to do it step by step. First, at 100 kilometers, you have the first characterization, and then you move to 60 with the information that you have gained. And then you refine your knowledge, and then with refined knowledge, you can go down a bit more, and so on and so forth. We were really doing this in steps, going down closer and closer, down to 10 kilometers at the end, and from where we managed to release Philae. And this is a very nice video that instead is a sum of images. We were taking images every 1 hour, and the comet was rotating below us, and this was how we were seeing the comet when patching together a set of images during several days. And arriving here at the comet was really one of the most interesting periods in our work, because we had to start doing landmarks, which I will describe now, and that was really an interesting phase. So in orbit determination, we said already that we basically use range and Doppler to communicate from to track the spacecraft from the ground with our stations. And but when we are close to a small body, this is not sufficient, because this does not give us enough accuracy in terms of knowing the position and the velocity of the spacecraft relative to the target. So for doing this, we take images. And after we take images, we look at the comet, at the small body. Actually, we will do exactly the same thing for ERA, which is going to go to a double asteroid in 2024. And we will do a similar thing also for JUICE with the Jupiter moons, actually, with the difference that instead of detecting landmarks, we will use a limb fitting technique, so fitting the limb of the moons, because the moons are more regular. They are all spherical, so you can use this limb fitting technique, and it's quite sufficient. But for this case, we had to do landmarks, which meant that we have to basically define a set of points on the comet, and these points are features like bumps or craters or ridges, some specific features that can make your eye recognize that point on the feature if you're doing manually. But not only your eye as a human, but also features that can be recognized by computer software, by automatic image processing software. And once we have defined a map of these points, like this one on the left, then at each new image, we can basically fit with our previous knowledge of these maps and understand what part we are looking at. So we have from each image 10, 20, or 100 or 200 even of these landmarks in the view of that camera image, and we can use this information to put inside the orbit determination together with the range and Doppler to constrain the solution and to find out with very high accuracy what is the relative position, the relative velocity of the spacecraft with respect to the comet. And then for the dynamic environment of the spacecraft, this is also quite challenging, because when you are flying around a comet, especially for an asteroid, is different. But for a comet, you have the drag. So the drag is basically the fact that the comet spits gases, because it's a comet, and these gases slowly impact upon the spacecraft. This is not a problem for safety, because it's low velocity, small grains and gases. But it is giving a force, an acceleration on the spacecraft, which acts together with the comet gravity. And the comet gravity, you can imagine for a body like this, is not a point. So it's not a very simple gravity field. It's a very complex gravity field, which needs to be modeled with relatively high harmonics. And then you have the gravity of the sun, the gravity of all the other bodies in the solar system, the solar radiation pressure. So you have a lot of these forces that act on the spacecraft, and you have to be able to tell them apart such that the orbit determination can fit the orbit and the dynamics in a decent way to reconstruct the trajectory of the spacecraft. But not only that, we basically managed to reconstruct within the same orbit determination filter the trajectory of the comet itself around the solar system, the attitude of the comet, how it is rotating, but also the positions, the exact positions on the surface of all the landmarks, and so on. So all of these things are estimated, and this makes a very big orbit determination problem. So usually for other spacecraft, we have tens of parameters that we estimate in the orbit determination, but for small body navigation, based on landmarks, we have thousands of these parameters. So this is all very interesting, and it works very well. It worked very well for Rosetta. All of this is done on the ground, and nothing. There was no autonomy on board for Rosetta. There will be a bit more autonomy, so a bit of these things will be done also by the spacecraft itself in future missions. But for Rosetta, everything was done on the ground. But what is very interesting is how you get to this image here on the left. So how do you define your landmarks, and how do you continuously and repeatedly find those landmarks on successive images? So you see here an example where there are these crosses, where each cross with a given color is a landmark, and we tracked these landmarks from image to image, like you can see here. So we did this first manually, and manually means manually. So we had developed a graphical interface where we could see images side by side, and we had to actually click one by one on these landmarks to say, okay, this one is the same as this one is the same as this one, and so on and so forth. And you have to do it for 24 images a day for months or years. So you can imagine that this is quite challenging in terms of manpower. We had a lot of functionalities in this buoy. We could zoom in, zoom out. We could change the contrast, and this allowed us to basically do this in a decent way. We could also see the same thing on multiple images, such that we could also observe the same feature that you see here from many different points of view to make sure that we were not making a mistake in the detection. But in any case, okay, and then we had to do the same when going down. So basically to still be able to match different, the same details, but in different levels of resolution. And so this was actually, when we got to the comet, we had to do this manually, and it was a lot of fun, really a lot of fun to do, because we had to sit down, print actually everything on a big table, and start to do, okay, this is a landmark, this is a landmark. We started giving names to the features of the comet, and this was really like, it really felt like seeing what we were doing, because usually in flight dynamics, although it's always a lot of fun, the work, we always just look at numbers on the screen. And for Rosetta, it was different. We could actually really see what we were exploring there. But after a while, after a few weeks, it already started to get boring, as you can imagine, and really time-consuming. So we had multiple teams of people working to do this job. But actually, we had already prepared for this, so we knew that this would not be feasible in the long run, and especially we would not be able to go very close to the comet with this method, because if you only see the full comet like this, you have enough of a few tens or a couple of hundreds of landmarks, and you can basically cover the full comet. But if you start going down at much lower distances, like this one, or even closer than this, because this was 30 kilometers and we went all the way down to a few kilometers in the end, then it becomes impossible, because you need thousands and thousands of landmarks, and this becomes really impossible for the human eye well, not the human eye, but for the human work to do this. So we had developed automatic image processing to counter that. And this is done based on what we call the maplets. The maplets are four-dimensional maps where you have the three-dimensional coordinates plus the albedo of each little patch of the surface. And this basically allows you, once you know the slope in 2 dimensions, and therefore the three-dimensional component coordinates, as well as the albedo of the surface, you can basically fully simulate how the image would look like, knowing the observing conditions. So knowing where your spacecraft is and knowing where the sun is illuminating from. And this basically, you just do an inverse problem. So you start from a flat plate, and you start with a lot of images. You start from at least 30, 40 images, and you let an estimator estimate these parameters of the maps. So basically to fit what is the best map to fit all the images that you have collected so far. And you just basically build these maps. And once you have these maps, you see this tiling of the surface. This is the real image, and this is the tiled image. Once you have these maps, then you can use them to correlate once you have new images, every time that a new image comes, you can extract from the image, this one on the left is from a real image, what this little map, little patch looks like in the real image, how it looks like in your simulation, and find the best correlation to see how far off you are from where you thought you were, and find therefore the measurement for where the landmark actually is in the image. So this is to be done thousands and thousands of times. So for each image, there's hundreds of patches, and for each patch, there is this cross correlation, and for each patch, for each image, you get a landmark measurements that then get fed into the orbit determination. So this was a lot of fun, let's say, to do it manually. Like I say here, initially it was a lot of fun, but it was very time consuming. So we went relatively soon. After a couple of weeks, we started phasing in this automatic maplet processing. You might ask why we didn't start with this, and the main reason is that we were not totally sure, 99% sure, yes, but not totally sure that it would work, because you know, automatic image processing is a complex field, and we borrowed the techniques from things that were not related to navigation in deep space, let's say, following also what NASA did before us for other missions. But in the end, the only way to be absolutely certain that this would work was to do a manual processing, at least at the beginning, especially because the shape was unknown. And it was a very good idea, actually, to start from manual processing, because with this weird shape, starting from scratch would probably not have worked. And also another important thing is that the features on the comet itself change with time, because with the outgassing. And also this is something that gives you the possibility of being sure with manual processing that you will be able to work, while with automatic method, it was not totally sure. So in the end, the automatic method worked really well, and we managed to use it for years. So after the first few weeks, we transitioned slowly to automatic processing, and this worked really, really well. And we managed, thanks to this, to get down to 0.5 meter resolution images. We built 11,000 landmarks almost. So you can imagine that this would be hardly feasible manually, especially considering, okay, I didn't put a million here. So this was 1.1 million validated landmark measurements in 14,000 images. You can imagine that doing this manually, one click or more per measurement, would not have been really, really feasible. So this was a real enabler for getting down to the very low distances from the comet that we had at the end of the mission. So these are just some examples of the other outcome of this work, which is the shape modeling. So from these patches, stitching them all together, this is a bit non-complete, but we had more complete cases. And we could basically build the full shape model up to very good resolution. So we had a global shape model of the full comet with a 5 meter resolution and a refined maps in some places, like the landing locations, down to half a meter. And you can see here, this on the left is a real image, and this on the right is what we would simulate based on that. So you can see that, okay, they're a bit different in terms of granularity and so on, but they're very similar. And this is just for fun, but not only fun, let's say. This was the escalation of our physical models that we were using in operation. So we started from the duck. And this was actually not for fun, because we really needed to have a way, due to this weird shape of the comet, to actually be able to understand where we were, see what we were seeing in each image. And we did use this duck with names of the different parts of the comets to be able to orient ourselves around the comet. But then, of course, after a few weeks, we could have a 3D printed model, first with raw and then more accurate, and then we were using that in the continuation. So yeah, now I want to go to the conclusion, so I will not show you a bit these details, but yeah, this is the end of mission part, and you remember the first image here, we had only a few landmarks at the beginning, and then we refined it with this automatic landmark processing to this one, which is what was needed at the end to be able to get down to our closest point, which was 3.9 kilometers from the center of the comet, which was basically just above 1 kilometer from the from the surface of the comet. This was really quite impressive to be able to get there, and we actually had planned to go even further. You see here the planned distance from the comet center in the last few weeks of the mission and what we actually flew. So we decided at some point to stop going down and stay at 3.9 kilometers because the navigation was not good enough anymore. We were risking that our prediction error would be too large, and therefore maybe we could have gotten closer, but then when we were closer to the comet, then our knowledge, our predicting knowledge on the position of our spacecraft would be too bad. And therefore, okay, maybe we were closer, but our instruments were pointed in the wrong direction. So we couldn't go closer because with this ground navigation cycle done on the ground, so there was no autonomy on Rosetta, so everything was done on ground. And doing things on ground, apart from being a lot of fun, also brings a delay, because all of this processing has to be done on ground and then send the commands to the spacecraft. So this delay is typically 1 or 2 days, and this results in a navigation limit, let's say. And we found out by doing, we had no idea, but we found out by doing that our navigation limit was here at roughly 4 kilometers. Then I had some more slides on the landing, but I think we can skip them. This is just for the fun. I've put some of the images of Philae going down and Philae as seen from the spacecraft here on the right, and Rosetta as seen from Philae. And okay, this was another really interesting part, but I decided that it would have been more interesting to show you what we do in flight dynamics, so this navigation and the image processing part, than just things that you can see everywhere else online. But I just put here some images because I like them a lot. So this was a very long campaign to search for Philae during the period when the comet was active. It was really active in some moments. This was really a lot of fun to see, and a lot of fun to see, but also kind of dangerous for the spacecraft. And not because big jets like this could damage the spacecraft, because again, these were just low velocity, small mass particles, but rather because we were flying with the star trackers. So the star trackers have to take images of the stars for Rosetta to know, for the spacecraft to know where it's looking at. And this is critical for everything, not only for science pointing, but also to communicate to the Earth, because Rosetta knows where the Earth is in inertial space, because we command the Earth ephemerides, so basically the position of the Earth. We send it from the ground to Rosetta, to any of our spacecrafts, but Rosetta needs to know where it's looking. And if the star tracker doesn't work because it's blinded by all the dust, then the star tracker doesn't work, then the spacecraft doesn't know where it's looking, then it doesn't know how to point the antenna to the Earth, and we lose contact. And if we lose contact, okay, this is the worst nightmare for spacecraft operators. We basically have to command the spacecraft in the blind, which means send messages, hoping that the low gain antennas, which are omnidirectional, can pick it up. And okay, this is really a nightmare scenario for operators, and therefore we had to retreat from the comet. You see here, this was the period during the perihelion pass of Rosetta, and you have here the spacecraft retreating up to hundreds of kilometers away. And only after a long while, months later, we managed to go back down to low distances. And this was just in time to spot again Philae. So almost two years, actually, after the landing of Philae, we actually finally managed to spot it on the surface with a NAC image when we were very close from the surface. And you can imagine why it's so difficult to see it, because here you have a 2.7 kilometers distance with a narrow angle camera, which is a very high resolution camera, and you can still see it only with this level of detail. So this is why it took 2 years to find Philae. Then we went down for the final landing of Rosetta, and that was the happy ending of the mission. And we flew down to here, which was an area that was of very high interest to the scientists. And Rosetta did its best. It managed to send images down to 15 meters from the surface, and then as soon as we touched down, we had set the onboard system, the onboard software to switch off Rosetta permanently because it was not designed to survive on the surface of the comet. So this was the end of the mission, and it was really a lot of fun. And I hope to have given you an idea of what we did in flight dynamics for Rosetta and what we did in flight dynamics in general for all our missions. Now, I don't think I have time to talk about other missions, but I have a few slides here of just to give you a taste of what's coming. So we have, again, already said Exomars. So this is already flying, and this one is flying soon. But to give you a taste of what's going to happen soon, or soonish, in the next few years for ESA deep space missions, we will have the Mars sample return. This will be probably the most challenging, or one of the most challenging missions ever for us, because we have to do a rendezvous in Mars orbit with the samples launched by the Americans with our Earth return orbiter, this one, which is in full control of ESA. So this was is quite a responsibility to catch the samples coming from the surface and going back to the Earth for the first Mars samples return. Then we have the gateway. We will also participate actively in the navigation of the gateway. So we are, okay, the navigation of the gateway will be a responsibility of NASA, not of ESA, because it's the main contributors are NASA. But we are going to do shadow navigation. So this means that we will do the orbit determination for the gateway in parallel to our colleagues in the US. And as they did before for us, for Exomars and for Rosetta, we will do the checkpoint, let's say, for their work on our end as well. So this will also be a lot of fun to follow. And this is just a contribution that Flight Dynamics is giving. Of course, ESA as a whole is giving much more to the gateway and the lunar exploration program in the coming years. And then we have also quite a lot of upcoming science missions. We are working on James Webb together with the Americans and Euclid, and the observatory, which is an observatory for dark matter, and JUICE, which will be also a lot of fun with Jupiter Moons Tour, even though this will only come in 2030, even though we launch in 2022, and more missions to come a bit later on. So, and ERA, I left it as last because I've started working on ERA a couple of months ago, and we are still in the early design phases, but this is also going to be really, really fun mission to fly, similar to Rosetta, but with much less money and more autonomy on board. So for some things, it will be even more challenging than Rosetta, and it will also have two CubeSats from managed not directly by ESA that will fly together, and we will go to observe the impact done by an American mission on the smaller of two asteroids in a binary asteroid system called Didymos. And the idea is that we are going to verify the deflection of that we managed to do with the NASA mission on the asteroid, on the minor of the two asteroids, for potential future needs in case of Armageddon style thing in the future. Okay, so sorry that I was a bit late, a few minutes late as usual, and I had to rush through the presentation as usual, but I never managed to put few slides in the presentations, and I could not see the chat, so I don't know if there have been many questions in the meantime, but yeah, feel free to ask anything, of course. And thanks for listening, if you may.
Okay, grazie, Francesco. Thank you, Francesco. Can you hear me?
Yes.
Okay,
yes.
During your presentation, I had basically my computer died because it was not correctly plugged to the electricity, so so I lost the batteries. And then I had some problems with the audio, and then now I changed the browser. So, I manage I use the contingency recovery procedures, the CRP, for this occasion. So,
Okay, but I hope you could hear, that everybody could hear me. I didn't.
No, yes, that was perfect. That was perfect. Somebody had problems, but it was on their side. And, okay. So thanks a lot for your presentation. Thanks a lot. There are so many topics. In fact, I got this wonderful idea. We may propose you something special. I will tell you that about privately, maybe if you are game for that. And you will decide after the question you are going to receive, because some of them are very interesting. I hope you are going to like them. So if you don't mind, I will go straight to the comments. There is one which has been voted by a lot of people, and this is got to the top of the list. And for me, it's very important because it highlights the fact that, of course, to go to work in your environment, you have to have a degree, usually in aerospace engineering or mathematics or physics, because you look a lot of mathematics and astrodynamics and a lot of things. But of course, you can enter in this job also with other expertise, of course. You can be a computer scientist, for example. You can be another engineer. You can provide support to these activities. So there is an entire, let's say, market, in a certain sense, of careers around that. So it's very important that people understand that coming to work in ESOC, also in the flight dynamics department, you don't have to be an astrodynamicist, but you can also be something else that is still useful to do the entire job, the jobs you do, basically. In fact, this question from Bill Atkins is very important. What programming languages do you primarily use?
Yeah, so this is what you said is very important. Okay, programming languages. We are in a transition phase, let's say. So the ESOC Flight Dynamics started in the 80s with Fortran, of course, because it was the language of choice for any scientific task at the time. And actually, it still is very, very efficient and scientific programming-wise, it's still very good. So our current code, the code that we still do operations with, is all Fortran. With parts with Fortran 77 even, which you can imagine is quite, if you know what it means, it can be quite a nightmare to maintain, and then other parts in Fortran 95. But we still use Fortran for all the operational software. And then we use scripting languages like Bash or nowadays more Python for kind of gluing language between the different software. But of course, this is not all. So since a few years, let's say 3-4 years, we have started a very big effort, which is to start from scratch and do everything again in C++. And it's not a trivial thing, because it's not only writing the software, it's also making sure that it works, and validating it properly takes years. So basically, we have started using C++, and we have redesigned completely our software from scratch. And now we are at the point, finally, that we are starting to do parallel operations. This means that we do our normal operations with the legacy software that we have been using for sometimes decades. And in parallel, on a different software platform, we are doing the same things all over again with the new software in C++ and Python. And this is because we cannot afford to go right away with new software. We have to have months of operations in parallel with different missions to make sure that all the outputs are consistent. We cannot just switch to the new one when we feel like it because the tests are passing. We really have to be sure that in all possible scenarios, the software is still giving the same results. So yeah, basically we're using Fortran plus gluing languages for the past, and C++ plus mainly Python for the future. Then there are some auxiliary tools written in more live languages like Mathematica, and but it's mostly C++ and Python for the future.
Okay, thank you. And it sounds like there is a lot of user interaction with data. How much automation versus human input intuition is used in flight dynamics operations? This is from Philip Costa.
Yeah, this is also very interesting. So I briefly mentioned it depends a bit on which missions we are talking about. So for Earth observation missions, there is a lot of automation because most of them are more, I don't say, they're not simple. They're just similar to each other, let's say, and for some things it's easier for those missions to make a nice automation system. And also it is critical for them to do it because they have a lot. For us, for interplanetary missions, it's a bit more difficult. Of course, you could automate a lot anyway, but sometimes it's not worth it because every mission is different. Every mission would require a different type of automation in a different way, and in any case, some things are left, as you say, anyway, to human intuition. So especially orbit determination is a science. You have to write the software in a very rigorous way, but there is also a bit of expertise and intuition that you always have to put in, and it's impossible to have a fully automated system for deep space orbit determination because there is always something new, something wrong with the data, something which you don't expect, some outliers that the software doesn't recognize, but you do. And so, yeah, it's difficult to give an assessment, but I would say that for Earth observation missions, a lot of the work is automated with just a human check at the end that the results are correct. For example, the orbit determination runs automatically, the Maoneuvre optimization as well, and you only have to check at the end that they make sense. For deep space missions, instead, the only automation is related to the mechanic tasks like processing data from the ground stations or, for example, this big part that I showed before about the optical data processing. And these things can be done automatically with a human check at the end. But for example, the orbit determination itself or the optimization of the maneuvers, or even the generation of commands, they can be automated up to a certain extent. And there you also have to evaluate mission by mission if it's worth implementing the automation, because it's quite a bit of effort to implement it. And if it's only for one mission, sometimes it's not worth it, or we think it's not. So yeah, it depends.
Okay, thank you. What are the various skills used or needed for successful orbit determinations?
Okay, this is complex questions. So for orbit determination, okay, the basic theory behind is mathematics. So in the end, if you have a background in mathematics or physics as well, is very important. Aerospace engineering is also fine. Let's say that the most important thing is that you are ready to learn new things, because in the end, you cannot really, when you get here, there's no way that you can know all the things that are required, and you have to learn on the job. So you must have the physics, mathematics, and the spacecraft engineering and software background to understand things. But yeah, you have to learn on the job.
Okay, I got a reply from Filippos about the previous question that this idea that this spacecraft would sometimes be the ones with the least autonomy is mind-blowing.
Yes. Okay. Rosetta was let's say, old concept, but it worked really well. But okay, it was designed in the 80s, so there was no autonomy yet. And we'll see how it goes with the new ones, because in the end, autonomy is nice, but you have to make sure that it works, and it's not always easy. So, and sometimes you have to tune the autonomy functions. So, for example, on Exomars aerobraking, we had a lot of autonomous functions on board, but it took us a long time to tune them such that they would work properly. So in the end, autonomy is nice, but not always, depends on the cases.
Yeah, yeah, there is, and then every agency has its own approach or industry to autonomy, so it's a little bit critical. Yeah. Can you comment on the type of testing and validation you do? Do you, for example, use formal methods for correctness proofs and so on? This is from Anthony.
Okay, I'm not sure what you mean with formal methods, let's say, but so basically we have different steps. The first steps are the first checking step is, of course, at software level. So our software needs to follow some standards. We have implemented things like unit tests and regression tests in the software that need to work. And whenever we do a new update of the software, we have to check that they still work. So this is the first level 0 checks, let's say. Then we have, for each new mission, we have in the preparatory phase, we have test campaigns that we do with the help of the test and validation team. So basically they prepare tests for us. They prepare test data and they prepare the scenarios and they give us the scenarios and the test data like if we were in real operations, but we are not. So this is all simulated. And we do the work as if it was real life, and then they check the results against their real world. So basically, this way they can verify that our solutions are sufficiently accurate for what is needed. And then the third layer, so this is the second layer during mission preparations. And then the third layer is the live test and validation, which was what I was discussing earlier. So basically, every time that we do something in operations, it is double checked by test and validation. So these are the 3 layers, and yeah, I don't know if this is meant as formal methods, but yeah, these are the 3 formal ways, let's say, of doing it on our side.
Would you say that? Would you say this from myself? Would you say that developing software for flight dynamics is a little bit more relaxed than for flight software? Because I worked on both of them.
I haven't worked on onboard software, so I cannot really judge this, but I guess so, because in the end, okay, I don't know, because we have to be very rigorous on our side as well. So it's, I don't know.
Probably you are more interested in computational reliability than software reliability itself. So basically, the software stack you can relaunch it. But,
yes, it's true that we are mostly not software engineers, so which means that we follow a bit less formal rules of programming. So we try to do that, but we do our best, let's say. And probably for onboard software, you have to follow different software engineering standards, which we only partially follow, let's say.
Okay. Now this a long one is complicated. Let me read everything. So the first question from Ferrat is that what is the orbit determination accuracy in position and velocity around the comet? What is the estimation technique that you use in orbit determination? Is it Kalman filter, least square, or similar technique? But also is a question on the delta DOR. I will ask the question delta DOR later. So answer first.
I see it. Yeah. So okay. Orbit determination accuracy around the comet, it's mostly driven by the accuracy of our camera, because in the end what matters most there is the accuracy in the landmarks measurements. With the Rosetta camera, that was 5 degrees field of view, 1000 by 1000 pixels. So let's say that we managed to get down to sub-pixel accuracy, let's say, and this resulted in usually a few meters in position and millimeters per second in velocity. But this again, this really depends on the scenario and the distance from the comet. It really depends on the different cases, the hardware of the spacecraft and so on. For different cases, we have different accuracies. In around a Mars orbit or a planetary body, you have the dynamics that helps you a lot, because you are bound by the dynamics of the orbit, which allows you to constrain the solution a lot. So also around Mars, just with range and Doppler, we get to meter level accuracy. That really depends on the problem.
I can confirm that on Mars reconnaissance orbits, there we get the position, the center of mass of MRO within the volume of the spacecraft.
Yeah, this could very well be.
Delta DOR?
For the estimation technique, okay, we use batch filters, which are kind of Kalman filters, but in the end they are not sequential, but they are all done at the same time. So all the measurements are processed at the same time. This is because we have all the data at the same time. We are not following let's say the timeline of the spacecraft. And I don't remember what was the last question.
The one was he wondered the accuracy of the delta DOR in finding angular position of the spacecraft.
Yeah, so okay, the delta DOR accuracy is really good. We are talking about nanoradians of accuracy, and this maps to usually a few hundred meters when you are at the distance of the Lagrangian point. And I say this because we use it for Gaia, because Gaia has very high reconstruction requirements, very high accuracy requirements for the reconstruction of the orbit. Gaia is 1.5 million kilometers away, and we use Delta Dor for angular measurements, and this is below, let's say, below 100 meters at that distance. Of course, it grows linearly with the distance, so it's a couple of kilometers when you are at Mars, for example.
Okay. Then I have a question from Nedelko, or probably Dan. Alin? Thanks you for the presentation. And what are the main assets used by ESA to collect optical data in support of orbit determination?
Optical data, you mean from the ground, so telescopes?
Probably yes. Probably yes. I know we use optical information with the laser ranging only for Earth orbital missions, of course.
We actually also use that for Gaia again. So for Gaia, we have some sessions with telescopes from, there's a telescope which is a couple of meters of diameter in Gran Canaria, I don't remember the name, and another one at ESO in Chile, in Paranal. And we take observations every night, I think, or almost.
Is it a passive observation, or is it laser excited?
No, it's passive. So just looking at the reflection on the sun shield of Gaia of the sun. And this actually, Gaia was supposed to fly without Delta Dor campaigns, so to be cheaper, let's say. It was supposed to use these optical data from ground telescopes for replacing Delta Dor, let's say. But then the actual visual magnitude of Gaia in the sky from the reflection on the sun shield was actually much higher than expected. So it was less bright in the sky than it was foreseen before launch. And this meant that we could not actually use only optical data. And also, it was planned to use a smaller telescope, like 60 centimeter diameter telescopes to see Gaia in the sky, but this is not feasible because of this. So we have to use bigger telescopes, these 2-meter telescopes, and we do use it, and we use this data as a complement to range Doppler and Delta Dor. In some cases, it's helping quite a bit, in others not so much, but yeah, we are doing that.
Okay. Are you going to use this optical method also for Euclid?
Good question. I don't know. I don't know very much about the Euclid orbit determination because I have not studied on that yet. I guess it depends on the accuracy requirements because Gaia has very, very precise requirements because they are looking at the asteroids. So they're not only looking at stars, they are also looking at the solar system bodies. And because of this, they need to know very accurately where Gaia is to within, I think, 100 meters because of parallax effects that you have otherwise if you're looking at a body which is not too far away.
Yeah. Euclid is more interested in the very far field with the galaxy.
Exactly. So probably Euclid doesn't have very stringent requirements, but I'm not sure. So
Euclid has incredible pointing accuracy. I work on the fine guidance sensor, so it's,
yes. But this is on board. This is amazing. The fine guidance sensors, indeed.
Yeah. Okay. Rodney has a question. Given that Mariner 6 and 7 flew past Mars in 1969, how accurately could flight dynamics estimate where they are today?
Mariner 6 and Mariner 7 flew past.
Maybe we should ask a JPL for this.
This is a good question. So the accuracy of where they are today. So, okay, I guess we have, not we, ESA, but somebody has the last orbit reconstruction of those spacecraft. That orbit reconstruction in the 70s was for sure much, in the 60s actually, was for sure much more crude than today. They didn't have Delta Dor, and also the range and Doppler data were of much poorer quality. But in any case, I guess that the prediction error now, after 50 years, is driven probably by by accelerations and acting on the spacecraft and propagating over such a long period of time. But to give a number of how accurately we could have them now, it's difficult.
Okay, I have a question. So, Rodney, if you write me an email with your address, I will ask my friends at JPL if they can answer this question. It's going to be interesting. Okay.
Yeah.
P. Rodney has another question. The Ariel mission to characterize 1,000 exoplanets will require efficient repointing from one target to another without having to wait for transits across the host star to occur. How will ESOC be able to automate an efficient process? Now, this is mostly... Yeah.
Okay, so basically
replanning pointings.
You need to point quickly from one target to another, no? You mean a star pointing to a star now, and then switch to point to another star in I don't know, half a minute, something like that. Okay, I guess that these things are usually driven by the agility of the spacecraft, because the deep space missions rarely have very agile platforms, which means that it takes usually quite a lot of time to slew the spacecraft, because it's spacecraft, relatively small reaction control wheels on board, because in the end they are just as agile as required, because to make it more agile, it means money. So bigger wheels, more cost. So in the end, the time required for a repointing is fully driven by the onboard systems. In terms of ground processing, whether we have an agile spacecraft that takes 5 minutes to do a slew, or a slow spacecraft that takes 2 hours, it doesn't really change much what we have to do. So we will anyway have to command these profiles, these slew profiles. Usually what we do is to generate on ground a discrete representation of the guidance profiles. This is usually done with polynomials, Chebyshev polynomials, that the spacecraft then interpolates on board to know what is the profile that it has to follow, depending on what we command from the ground. And this process can actually be automated quite well. So for some missions, this is even for our deep space missions, for example, Exomars, this is basically automated. We receive inputs from the scientists in terms of point there. For Mars, this is Mars, so we are receiving inputs in terms of coordinates on the ground. But for Ariel, it will be inertial pointing, right ascension and declination, for example. We receive them from the scientists. And it can be automated quite easily to translate these via automatic software on our flight dynamic system into Chebyshev polynomials to describe the slewing profiles. So the efficient repointing, I don't think it will be driven by ground processing. It will be driven by the mission, by the spacecraft design.
Okay, thank you. From Yain, we have a question. How closely do your team work with the launch services provider when working on orbit determination?
Not so much in the end, because from the launcher team, we only need mainly an assessment of the launcher injection accuracy. This is needed because we need to know up to which point we can trust the pointing profiles that we send to the ground stations. So the ground stations, so we, Flight Dynamics, based on the planned launcher trajectory, we have to generate files that will tell to the stations how to follow the spacecraft. And our antennas, each of them has a beam width. The smaller the antenna, the larger the beam width. And we have to assess whether the launcher will be within the beam width of the antenna or not, depending on both the nominal trajectory of the launcher and the nominal injection accuracies of the launcher. So this is basically it. So they have to tell us where they will launch and with which accuracy. And then this is before launch. And there are a bit more interactions usually with the mission analysis team, which is the team that have to do the mission design. So not the operational phase, but the mission design years in advance. and then they have to know a bit more details from the launcher authority, like all the reference frames and these kind of things. And for us, in terms of operations, the only thing that we do live in operations is to receive, after the launch, fax. This is still done with a fax. It will change at some point, maybe. And a fax from the launcher authority that tells us what are the reconstructed injection parameters. So basically, after they have tracked the launcher, because the tracking of the launcher is done by them, not by us, they send us a fax with information on the state vector at separation of the spacecraft. And we use this to basically do a quick cross-check that these files that we had sent before launch to the stations to tell them where to point, we have to quickly check if with the real launch, we are still within the pointing accuracy of those files that the stations have. And if we are not, then we have to update those files based on the fax that we receive and give it to them again, such that they don't lose the spacecraft. So yeah, this is about it. Okay.
So basically, how long it takes if you get a situation in which you don't find the spacecraft in the position it was supposed? How long it takes to recompute everything with the state vector and then send the information to the ground stations?
This is very quick. This is very quick because it's all is ready, and we can probably do it in a few minutes. But of course, there is a series of steps that need to be validated. So usually we take maybe 2 hours in terms of time before delivery. So we always take margins on margins and margins. And this is always a good engineering rule. Okay. This way you also seem nicer, no? So you say 2 hours and then you do it in 1 hour. And
yeah, of course. And just for you to know, Rodney wrote that he wants to bring back a Mariner 6 or 7 or both. He wants to bring back and to show them at the Science Museum. That's why he was wondering about tracking them. So good luck. I'm completely go for it. I'm completely okay. So how large are your dev and test teams? Do you use the agile development methodology?
We started a bit. So let's say that we are no. So I don't think we can say that we use agile development. But we have at least started with this latest software development that I was mentioning before. We are doing a bit more modern software engineering. So basically, we are using fancy things like GitLab and all of these interactive features that you have there with the Git repositories. And we are doing kind of sprints in terms of development and very frequent design sessions, let's call them, for specific pieces of the software, but it's not really formalized. So I actually haven't ever followed a course on agile development, so I don't know actually very accurately what it means. Let's say that we do it a bit more our own way, but following using modern tools and modern standards. Okay.
In a certain sense, I think you are more agile than a standard development. I'm pretty sure about that. In the
yes, indeed.
How do you make sure your system are safe after years of staying dormant? And just a moment, I lost it. And how do you still make sure the antenna is pointed at Earth when you turn the system back on? I would imagine reaction wheels are quite power intensive, cold gas consume fuel, interplanetary costs, and so on. This is from Sam.
Okay, this is again fully spacecraft dependent. So every spacecraft has its own approach, let's say. The only mission that we had so far that has a hibernation, a deep space hibernation, is actually Rosetta. No other, all other missions don't have this hibernation phase. Rosetta needed it because they didn't want to oversize the solar arrays for the apohelion part. For Rosetta, okay, how to make sure that the systems are safe after years of dormant? I don't really know. You would have to ask to the designers of Rosetta, because it worked, and it was a very, very tense moment when it was about to work, because we were there waiting, and we had been working for years on the development of this nice optical image processing and so on. And if it had not worked, then nothing would have been it would have been completely useless. But you have to ask to a designer how to make sure that they still work. In terms of antenna pointing, it's okay. The spacecraft, the antenna is not pointing to the Earth during the hibernation, of course. But when the spacecraft revives after the hibernation, the first thing it does is to switch on automatically the star trackers. And with the star trackers, it knows where it's oriented in space, and then it has saved in the safeguard memory of the spacecraft the Earth ephemeridis that we have commanded years in advance. So these stay in safeguard memory. So even if there is a full reboot, they're still there and they can be copied again to RAM. And then it uses this information together with the knowledge on the attitude from the star tracker to orient itself to point the antenna to the Earth. And the reaction wheels are indeed not used during hibernation, but they are switched on again after the hibernation ends. So during the hibernation of Rosetta, there was actually no active attitude control at all. It was a spinning and everything was off. So the thrusters, the wheels, everything was off. So the only thing that was on was, I think, the onboard computer, but only in a special mode, which basically had nothing active except for some heaters to keep thermal control active such that it would not freeze.
Yeah. Paolo Ferri told some weird things happening about that.
Yes,
so
yes,
they were
yes.
unexpected, let's say. And,
it was interesting.
Yeah. And safeguard memory, for people who want to know, safeguard memory is a special memory inside the onboard computer that is stores also not only the ephemeris, but also stores timeline of commands that can be used in special occasion in emergency situations. And a basic configuration of information for a basic configuration in the spacecraft. Okay, so from a more, Francesco, we have to close this in basically 6 or 7 minutes, and because we have a time and things. So very quick on the last few questions, 5 questions. From a more professional approach rather than technical, how do you tend to approach unknown challenges during the mission?
Unknown challenges. Okay, they have
surprises. Let's call them surprises.
Okay, you have to try to plan for everything if possible. Of course, you can always find something that you don't expect for, and in that case, okay, it's actually very rare that there is something that you really didn't plan for. So even this Rosetta shape, we actually had planned for it, because, okay, not for this specific shape, but we had decided to go with the manual approach at the beginning, especially for this reason. And okay, you might have other unplanned things, and then you have to be very well aware of what your tools are, very well aware of what you can do, and use your imagination when you get there. But it's from a professional approach, let's say, it's very important to think in advance of everything that can go different from your nominal plan. So you always have to think very carefully about off-nominal situations and try to have very, very simple methods. So it's always good to choose the simplest method that allows you to fulfill the needs of the mission. So never go for something which is more fancy than needed, because it might not be robust enough to unknowns, let's say. So I don't know if it answers your question.
Okay. Does ESA plans to answer questions relating to the development of world colonization, like living on the moon to prove and validate technologies before going to Mars? Actually, ESA is not very talkative about this. But
yeah,
do you have any feedback?
I don't know, and I don't think I can speak for ESA in this. So
okay.
it's a question for people about a bit above my place, let's say. Sorry.
Peter, yes, I suggest Peter to post again this question when we have this meeting with Tiago Loureiro, which is the flight director of Exomars.
Yeah, maybe you can ask. We can try to ask. Yeah.
Maybe Tiago is going to be able to answer.
I mean, it depends on which questions, and there is a PR office for ESA that has to answer these specific questions. So
okay. And I have a question for myself, actually, is it about the surprise? You already answered, but basically when you saw that the peculiar shape of the comet, how critical was that discovery? Because, of course, you didn't plan it.
Let's say that we thanked a lot our boss at the time that decided that we should not go for the automatic approach without, because we were, all the young people were saying, this automatic thing is super nice, it will work and so on. But in the end, it was a very good idea to start with the pragmatic, simple manual thing. So it was not, we were not scared because we were surprised and actually amazed by the shape of this thing, because it was the first time that anybody had seen a shape like this. But we were not really scared because we knew that with the manual processing of the images, I mean, in the end, you just have to click on the landmarks and the shape is, doesn't really matter. So we had some doubts that the automatic image processing would work, but we knew that by providing an initial guess of the shape that we would build with manual methods to the image processing, then it would probably work, and we were more curious to see how well it would work rather than scared that it would not.
Okay, thank you. How much contact does your team have with flight operations teams at NASA and other agencies? Have you learned any lesson from each other?
With the flight dynamics teams of NASA, of JPL in particular, we have a lot of contact, and we do have a lot of lessons learned from each other. And we actually have regular teleconferences with JPL, with let's say the people that do the same job that we do for the NASA JPL missions, like the Mars missions or the outer planet missions or whatever. We have regular monthly teleconferences with them to update each other on the status of our projects and to have to basically define the status of the tracking of the different spacecraft and to see if we have questions or any other topic of interest can be discussed and so on. And then we have dedicated campaigns in some cases, like the Rosetta comet phase and the Exomars aerobraking, where we actually do much more frequent exchanges. And I have to say that so far we have learned a lot from them, because we have also validated our software against theirs because they have done things first. But lately we have also started to reciprocate a bit, because for Rosetta, we learned from them, but they also learned a bit from us because they had never been to a comet before. And also for the aerobraking, in the end, learning how we did things, I think gave also them some hints on some things. So it's, I think it's a reciprocal thing, even though, of course, JPL started this whole thing before us, and we are using their expertise probably still a bit more than what they use ours.
Okay. It's still nice to know that there is this cooperation. It's very important for everybody.
Yeah, it's amazing, actually. Yeah.
So Diana says, great talk, and do you ever had difficulties following some powerful solar eruptive events? So did you, dynamically speaking?
Dynamically speaking, not really, but the star trackers are sensitive to, so all electronics equipment on board any spacecraft is sensitive to solar events, but the star trackers are the most sensitive, especially the older generation of star trackers. And we did have a period of, I don't remember, probably 1 or 2 days over both, I think, for sure Rosetta and maybe also Max, where the star trackers were blinded by the radiation coming from a solar event. So it's not really, so this was still within the limits of what the spacecraft could do, because it can propagate on gyros the attitude for a while. But yes, solar events are always a concern for onboard electronics.
Of course, yes. Thanks, Francesco. The question around, no, maybe there is just one more question. No, I don't think so. No, it's done. Thanks a lot, Francesco, for your time. Alistair is
welcome.
Yeah,
you're welcome.
I hope you can hear me all right.
Perfect.
Yes.
Oh, good. I normally sound like a chipmunk at this time. But thank you very much, Francesco. What an amazing talk. I'm amazed how much you covered in that 1 hour. Incredible. I still don't know much about flight dynamics, but I'm afraid that's my problem. Your detailed answers were fantastic too. And I see from the chat here that we had 225 people on board. And I worked out that we had people from 8 or 9 different countries and I think 24 different places. So quite a cross section of the population. But I must also thank Fabrizio for doing all the introductions and for coordinating the Q&A. And thanks also to Elizabeth for coordinating the event behind the scenes. It seems to have run quite well so far. If you've enjoyed tonight's talk and want to make a donation, please click on the donate button. Every little helps to cover our costs. Now, looking quickly at some of the things we're planning, on the 8th of April, we'll be attending the MANSEDS conference at Manchester University. Of course, it's virtual, so I'll be there in spirit and I hope online. And then on the 9th of April, we'll be launching our next generation network. Now, this is a new thing for us. This is for 18 to 35-year-olds and is an initiative led by our younger members. So we'll have something interesting to say on the 9th of April. Then on Monday the 12th, I've already told you about Beyond the Moon Symposium and the Uris Night celebrations. But remember, it's also the 40th anniversary of the STS space shuttle. So look out for an announcement in the next couple of weeks of an event to celebrate this later in April or May. On the 28th of April, I'm pleased to say that Fabrizio has found us another excellent speaker, Tiago Lorerio. Have I pronounced that correctly, Fabrizio?
I don't really know. I hope so.
Loureiro.
Lorerio. Okay.
Loureiro. Yeah, it's a Portuguese guy.
Okay, I'm glad you got that one for me. Now, he's the Exomars ground segment manager and also the Exomars rover and surface platform flight director at ESA ESOC. Is that with you as well at Darmstadt?
Yes.
Yeah, thought it was. Yeah. So he's going to tell us all about Mars on the 10th of June 2023. Now, I assume that's a significant date for ExoMars 2022, the Mars rover. Is that correct?
Mm-hmm.
Yes.
Right.
Yes, we are landing.
I look forward to that because the last time I sat in on a press conference was the Beagle 2 one. So sadly, that wasn't as great as
maybe you know, Alistair, maybe we don't want you at that event.
I had nothing to do with it. I was just the PR man. Going a bit further on then, 28th to the 30th of June, we of course have the Reinventing Space Conference. Now that is definitely on. We hope to be live in the QE2 Conference Center. So please start booking your tickets now. It's online and you should be able to see the program shortly as well. Finally, I'd like to say thank you to a lot of people who have put in a lot of time and effort into getting the Sir Arthur Clarke Awards up and running. And I've got all the judges' votes in yesterday and today, I hope. And we'll have results for the finalists within the next couple of days. And then we go for the main presentation to the awardees on the 29th of June at the QE2 Conference Center. So thank you all for a great evening. And thank you for those that actually made the effort to listen in and also to do the presentations. It's been a tremendous evening. Thank you very much to all and good night. We'll see you in the next week or so. Night all.
Bye, everybody. Thanks, everybody.
Bye-bye. Thank you.
Thanks a lot.
Bye-bye. Bye.
Goodbye.
Bye-bye.